Okay. So right here, the last time we met, we had talked about the Lewis structures, which was Monday. Today I'm starting with resonance structures and then formal charges and going on from there. So here's the thing. Once you draw your Lewis structure, based on following the rules, different people can come to different Lewis structures. Sometimes when you follow the rules, you may end up with the best Lewis structure that possible is, and then somebody next to you can follow the rules, but then kind of end up with a not the best, but a decent Lewis structure. So how do you look at two Lewis structures and decide of all the Lewis structures you're seeing, which is the best? One of the issues with Googling Lewis structures or Googling stuff on the internet is sometimes you get more than one quote unquote correct answer for your question, yet you know that there's only one possible choice, right? So you're trying to figure out which one is the correct one. Usually the one that's correct follows all the rules. Not only that, it follows the natural behavior of chemicals. So we're going to be going through this, but instead of just kind of guessing which is the right one, we're going through rules that will help us pick the best Lewis structure. So we're told here, the topic being resonance and formal charges, two additional concepts to write the best possible Lewis structures for a large number of compounds are covered. First one is resonance, second one is formal charge. What is resonance? Resonance, the terminology is used when two or more compounds or two or more valid Lewis structures can be drawn from the same compound. So you have one compound or one formula, and then you and the person next to you draw two or more. Now the rule here is valid. So both of them are valid. You go through the rules to test for validity and you conclude they're both valid. So which one is the more correct one? If they're both valid, which is correct, we'll use the Lewis structure to figure out, or the resonance rules to figure out which is more valid. The other concept, formal charge, is really the best way for us to figure out which is the best Lewis structure. With formal charge, you have an electron bookkeeping system that allows us to discriminate between alternative Lewis structures. So with this one here, you haven't necessarily concluded that all the Lewis structures are the best. You just realize all the Lewis structures are possible, but the question for the second one is which one is the best. So we'll go right into this. To explain resonance, resonance is a condition that exists. Now, the term resonance is used in physics. If you've done resonance in physics, we're not talking about that kind of resonance. We're talking about resonance in the context of chemistry. So Lewis's bond localizes the electrons between the atoms that are bonding together. This is another way of saying that electrons in a bond. So remember, when we're drawing the Lewis structure, let me give you an example. Say hydrogen and hydrogen are forming a bond. If they're forming a bond, remember I mentioned earlier, two electrons equal one bond. It takes two electrons to make one bond. So if the two hydrogen atoms are forming a bond, the hydrogen on the left brings its one electron, the hydrogen on the right brings its one electron. The two electrons that are brought are then combined to make a bond, right? And so Lewis's theory localizes the electrons between the atoms that are bonded together, which means that Lewis's theory localizes means local, right? You can't define a word with the same word. It just means concentrated in, it's fixed in a certain area. When you say something is happening locally, you mean it's happening at a specific location and not somewhere else. So in other words, let me use a different word. Lewis's theory restricts the electrons between atoms that are bonded together. So the bonded electrons are restricted between the two hydrogens. They can't be anywhere else because they're the glue that hold the two hydrogens together, right? So when they say localizes, they kind of mean restrict. It's interchangeable words. Extensions of the Lewis theory suggest that there's some degree of delocalization. Ooh, that when you look at other theories beyond Lewis's theory, such as resonance theory, the resonance theory shows that electrons don't necessarily have to be stuck. Not all the electrons have to be stuck between the bonding elements. Some electrons are able to kind of spread beyond the bonding elements. Okay? So we're told here some degree of delocalization. So delocalization is the opposite of localization. If localization is to restrict, delocalization is to reduce the restriction, right, of the electron. And this concept is called resonance. So delocalization of charge helps to stabilize the molecule. Oh, so here's the rationale. Okay, so scientists are saying when they see molecules delocalizing their bonds, the molecules are trying to be stable. Remember the rationale that scientists give molecules for their strange behavior or their unusual behavior is they have goals, and one of their main goals is to be stable. So elements, molecules do a lot to be stable. So here we're being told one of the ways in which molecules become stable is by spreading out the electrons. Delocalizing will be like spreading out over a bigger region, kind of like I don't know, my mind right now goes to kind of I guess when I was learning this, let me say what how I thought of this when I was learning this. I thought about spreading the burden, right? People say when you're going through stuff in life, share your burdens with other people. It makes it easy to carry your burdens. And I'm like, okay, what if they don't want it? But the electrons are spread out between more than just two elements, and this helps with stabilizing the molecule. Okay, so when there is more than one Lewis structure for a molecule that differ only in the position of the electrons, they are called resonance structures. So let's see how this plays out. Example, the actual molecule is the combination of a resonance structure. This is called resonance hybrid. So I will come back to this conclusion because this is really more of a conclusion, right? Let's see how resonance structure plays out. There's so many conditions in which resonance structure plays out, but in general chemistry, where we're kind of introducing this concept, we'll look at simple forms of resonance. If you go into organic chemistry, you will pick this up and take and go into this even deeper and learn about more resonance structures. Okay, so here we're just learning. And so I'll tell you this, at you guys' level, the way to see resonance structure is when you have a situation like this in the ozone molecule. So let me go ahead and build this ozone molecule from scratch using the Lewis structure. We're going to be drawing O3. Okay, this is ozone. Ozone. Okay, so O3, when we're drawing O3 with the Lewis structure, you want to write your central atom. Now it's O3, so we have 3 oxygens. So just pick 3, your central atom, 1 oxygen. The other 2 become your peripheral or your surrounding atoms. Now let's do our count for our number of electrons. I'll do it on top. Our element seen here is oxygen. We have 3 oxygens. Each oxygen to the structure is bringing in how many electrons? 6, right? And it's in group 6. It is 6. So with each oxygen bringing in 6 electrons, because it has 6 valence, 3 times 6 gives us 18. So in drawing our Lewis structures, we're working electrons. I'm trying to find my periodic table right here. Okay, right there. Yeah. So with 18 electrons, we follow the Lewis structure rules. First thing we do is draw a single bond between the central atom and the peripheral surrounding atom. Central atom right here, single bond, single bond. Okay, each single bond uses 2 electrons. Remember, 1 bond equal 2 electrons. So I've used 2 electrons here, I've used 2 electrons here. Now, okay, 2 electrons here, 2 electrons here. Now, where are we? Yeah, so we have used 4 electrons total. We're left with 14 electrons. Okay, so with 14 electrons, what do we do next? Once you're drawn the single bond between the central atom and the peripheral atoms, the next move is to make sure the outer elements have octet. Make sure the outer elements have octet first before you try to place any electrons in the central atom. So I made up this word, octetify, like make sure the outer ones have octet first and then the inner ones can have the remaining electrons. So we make sure they have octet by adding 6 electrons to each other outer element that is not hydrogen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. For my electron bank or reservoir, I remove 6 twice, that's 12 minus 12 electrons. I'm left with 2 electrons. My remaining 2 electrons now go on the central atom. You always fill the central atom last. Dot, dot, minus 2 electrons. We are now at 0. Make sure before you try to double bond that your electron bank, electron reservoir is empty. Don't try to double bond when you still have leftover electrons. Okay, so I do my octet check. I got 6 electrons in dots and then 2 in bonds. So there's 8 electrons here, 8 electrons here. When I look at my central oxygen, I have 6 electrons. Okay, so we don't have octet. The goal in drawing the Lewis structure is for elements that can be participate in octet to get an octet, which is 8 electrons. So because I don't have an octet here, now I have a choice. The rules say that if you're trying to help the central atom get to 8 electrons, you can either use, in this case here, we have oxygens on the left or the right. The oxygen on the left has lone pair electrons that can be shared, and the same thing with the oxygen on the right. So which one do I select to help the oxygen in the middle? Doesn't matter. I'm going to do it 2 different ways. One way I'll draw it here, the other way I'll draw it here, okay? So the one on the left, I'll use the lone pair from here and share it between these 2 oxygens. So I end up with this structure right here. Oxygen in the middle, oxygen on the left, single bond, up, up, up. Nothing happened to the oxygen on the right. Now I have a double bond here. My lone pair is still there. And then this oxygen on the left now has 2 lone pairs remaining to itself. So what I did in this process here of sharing the electron, I took the lone pair electrons. These are lone pair. So these would be electrons that used to belong to the oxygen on the left only, and I shared them between the one on the left and the one in the middle. Now these bonds are shared as a bond. The electrons are now shared as a bond, and they belong both to the oxygen on the left and the one in the middle. Okay. In the scenario on the right, I am doing a different approach. I'm actually taking this lone pair here and sharing it between these 2. Okay. So as to not be confusing, when I'm doing the one on the right, that implies I didn't do this part here. Okay. If I'm doing this part on the right here, I'm doing the opposite and having the oxygen on the right be the one rescuing the one in the middle. So this time here, the double bond is formed between the right and the middle. So single bonds are still there. Lone pair is still here. This time nothing changes on the left oxygen. The one on the right is the one that's being forced to share its lone pair electrons with the oxygen in the middle. Okay? So after I've done this, here's the issue. In exploring all the possibilities, I have 2, what I would argue, equal Lewis structures, equally valid, right? I think the left one is just as valid as the right one. So let me do an electron check. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. 8 electrons. Last one, 8 electrons. See, the middle one has 8 electrons. How does it get to that? It has access to 3 bonded electrons, right? 1, 2, 3. Each bond takes up or houses or holds 2 electrons at 6, and then a lone pair up here. The one on the right has 3 lone pairs, 6 electrons, and then 1 bond. So yeah, same thing here. A, A, A. So we have an octet of electrons for all the atoms in the compound, and everything looks good. Okay, so which one? Oh yeah, what do we have going on here? So we are told, back to the resonance structure, we are told that both, I'll call this Lewis A, okay? Lewis structure A and Lewis structure B are essentially alike, right? They're not the same, but they're alike, okay? Now, when I was a student, I'm like, no way. I mean, I didn't tell my teacher all these comments that were in my head. I had like I usually have an ongoing dialogue, an ongoing commentary of everything I'm seeing in my life in my head. So I'm like, no, wait, these are literally alike. And then the teacher explained, they're not alike. And let me tell you why they're not alike. In the world of chemistry, environment matters, right? So let's say the oxygen on the left is oxygen number 1. This is number 2, and this is number 3. Same thing here, number 1, number 2, and number 3. Imagine you're on the phone and you are describing these two ozones to a friend on the phone. And you're trying to describe, well, and then on the Lewis A structure, the double bond is between, and you will conclude, oxygen 1 and 2. The oxygen on the left, and then the one to the right of it. So oxygen 1 and 2, that's where your double bond is, right? And then for Lewis A structure, the single bond is between 2 and 3. And then you say, and then on the second Lewis structure called Lewis B structure, the double bond this time is between oxygen 2 and 3. You see how that makes it different? You stated that the double bond is between two different oxygens. So here the double bond is between 2 and 3. Here is between 1 and 2. And that's how they are different. The environment of 2 and 3 is not the same as the environment of 1 and 2. And this time for Lewis B structure, the single bond is between 1 and 2. So by virtue of that, in the world of chemistry, these are different. Okay, while on paper we can show that we have two different Lewis structures, first of all, Lewis A and Lewis B structures are resonance structures of each other. And there's a special arrow that is used to illustrate resonance structure. This is the arrow. So this is the arrow pointing to the resonance arrow. And this is a resonance arrow. So in chemistry, in the world of chemistry, this arrow is left for, it's used uniquely for the resonance structure. So when we use this arrow, when we see this arrow in a paper, in somebody's communication, we're like, oh, resonance, right? Like when you see laugh out loud, apparently somebody is laughing out loud, even when they're not laughing out loud, right? It's symbolic. When you use that, you mean resonance structure. So then we look for resonance. Okay, not only that, remember, Lewis A and Lewis B structures are resonance. Oh, now I can't spell. Resonance structures. Okay, took a few tries there. They're resonance to each other. Okay, but remember back here, they said something blah, blah, blah. The real structure is a resonance hybrid. What exactly is a resonance hybrid? So they don't show that here necessarily, but the resonance hybrid is like a hybrid as we know this. Oh, they showed in the next page. I just realized that. As we know of hybrids in a car. When you say a car is a hybrid, which I do have a hybrid, it just means that it's a combination, it's a fusion, right? It's a combination of two different things, right? So in this case, you have Lewis A and Lewis B resonance, right? And then I'm going to draw the resonance structure or resonance hybrid. So in the hybrid, the resonance hybrid, this actually shows the delocalized bonds. Okay, so that is the purpose of the resonance hybrid. Okay, it shows you the delocalized bonds, the bonds that are spread around and stretched over more atoms than what we expect. So I'm going to tell you this: when you're drawing the resonance hybrid, you are only allowed to spread out. I shouldn't say you're only, but yeah, you're allowed to spread out lone pair electrons if possible, or you're allowed to spread out the second bond, the double bond. So to keep it simple, because we are only learning so much and we're just introducing this, I'm going to just say spread the second bond or double bond. It's not really both bonds, just the second bond. I should say the second bond in the double bond. Second bond in the double bond. Okay, once again, I'm trying to remind myself we're not learning organic chemistry here, so I'm going to stick with general chemistry. We are only learning this one way. When you get to organic chemistry, you learn all the different ways you can spread a charge, you can spread a negative charge, an electron, all that stuff. We're just learning this one thing, to spread the second bond and double bond. So what I mean by that is we are drawing our resonance hybrid. The positions of the first, second, and third oxygen remain. So I'm just going to draw it like this. First, second, third. Okay, so I'm not scrolling back and forth. I'm going to draw the first ones here just so you can see the resonance A, resonance B, single bond, single bond, single bond, single bond. I had a double bond here, I had a double bond here, dot, 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 and then 1, 2, 1, 2. Okay, so I call this resonance A, this is resonance B. So now we're combining these to make the hybrid. In the hybrid, we tend to not include the lone pairs on the outside. The single bonds remain as is. Okay, the single bonds are the first bonds that connect the elements. Those are necessary to keep the compound intact. So in looking at the oxygen 1, 2, and 3, 1, 2, and 3, the position don't change. 1, 2, and 3 is still where it is. The single bonds remain. The only thing that spreads around is the second bond of the double bond. So I'm going to highlight it here so you can see. This is the one that spreads around. I'm talking about this one here. Okay, so I'm going to take one bond, right, the second bond, and spread it between 3 atoms. Okay, so when you spread a bond, how do you show that? Because it's not an intact bond anymore, it's kind of pieces of it. We show it like dotted lines, like this. So half of it goes there, the other half goes there. And so this is considered the resonance hybrid. So this is called the resonance hybrid. Okay, so please notice where the dotted lines are. The dotted lines are where your double bond used to be, right? On the left-hand side, the double bond was here. So you see the dotted lines here. On the right side, it was here. So you see it here. Okay. Then while we're looking at this, so how does scientists know if you can draw on paper resonance A and resonance B? How does scientists know and prove that the resonance hybrid exists? And not only that, they also said the real ozone molecule is a hybrid. So technically, ozone exists in hybrid form. Okay, if you were asked to go and get ozone from the atmosphere or to make it in the lab, when you make it and you generate it, it will exist in the hybrid form. It only picks one form, resonance A and B, right before it reacts. So compounds delocalize right before they react with something else, because to react in this form is kind of like, it's complicated. So when they're naturally existing, they're stable, they exist in the resonance form. If they're about to react, right before it reacts, something changes in the molecule to localize the bond, and then that allows the bond to break, and then combination happens. Okay. So while we're here, scientists did experiments, and they noticed the existence of resonance structures. So what happened? I'm going to give a quick illustration to show how they proved this. Let's pretend, okay, I'm going to assign numbers to the bond values, because bonds, single bonds are longer, double bonds are shorter. Single bonds are weaker, double bonds are stronger because you have more bonds. So I'm going to use bond length to show you the difference. Let's say the single bond, which is longer, is about 2 centimeters long. Then the double bond that is shorter is 1 centimeter long. The actual lengths are different numbers because they're very, very small, right? Tiny, we can't see them. Okay, so scientists were doing experiments to measure the bond length of ozone in its resonance form, in its hybridized form. They were expecting, before they realized it was in the hybridized form, they were expecting to get 2 results for the bond length. They expected one to be 1 centimeter, which for them will prove the existence of a single bond, right? And then the other answer they're expecting was 2 centimeter, which will prove, we have a double bond. Okay, so they were measuring, which for the most part, when you're doing a science experiment, you want to have a hypothesis. You want to kind of not really guess the outcome, but you want to make an educated guess of the outcome. So when you're going to the lab, you're trying to prove yourself right or wrong, right? So they went in there, and their hypotheses were, we know what we'll get for our answer. We'll have 1 centimeter, which will prove a single bond, 2 centimeter, which will prove a double bond. Let's go ahead and do the experiment. They did the experiment, and they were very wrong. They didn't get 1 centimeter. They didn't get 2 centimeter. They got one answer, and the answer was 1.5 centimeters. And I was like, wait, what? 1.5 centimeter? That wasn't the possible answer we had. First of all, we don't even have a bond length of 1.5 centimeters. We have 1 centimeter, we have 2 centimeter. What is 1.5? So then they have to work backwards, right? And of course, the numbers they're working with are not that simple. They have to work backwards. They have to try to explain the result. First of all, they repeat the experiment to make sure the results are correct. Once they get the results, they try to explain it, and they realize 1.5 is halfway between 1 and 2. So they didn't have clean, neat bonds. They had a hybridized situation, right? Neither 1 or 2 bonds. So they concluded the first bond was intact, right? The first bond, the original one was intact, but the second one was in pieces. So what you have here is 1.5 centimeters and 1.5 centimeters. So it's a hybrid of the situation. Okay, so it's a hybrid, something in between the two. So it's like taking 1 plus 2 divided by 2, right? So it's neither 1 nor 2, but this is how they draw it. So the single bond being intact, the second one being like that. So I feel like I've over-explained it. They use the illustration here of dogs, which when I first saw this book, I was like, huh? Because back at home, we don't breed dogs. They just kind of do their own thing, and then they show up with puppies. So I was like, what is this? Anyway, I got somebody explained to me, and I got the concept. Okay, hybrid dogs. Anyway, here you have the original Lewis A, you have Lewis B, and then they're telling you this is the actual ozone molecule. When you're drawing the resonance hybrid structure, you don't usually include the lone pairs here because it's kind of the purpose of this structure is to show you which bonds are delocalized, right? So only the second bond is spread around. So we're told here resonance hybrid structure is intermediate between the contributing resonance structures. So Lewis A and Lewis B contribute to form the resonance structure. Okay. So here we're told write the Lewis structure for NO3 minus ion, nitrate ion, include resonance structure. I'm going to add something to this question and say not only include all the resonance structures, I'll say and the hybrid. Why not? Let's go all the way. We've come this far. Yeah, this chapter is kind of long. So we got nitrate. We're going to draw the Lewis structure. After that, we're going to do the resonance hybrid. Or resonance hybrid. Okay. So let's see. Let's start from the beginning. Nitrate. With nitrate, I have 1 nitrogen. So I put the N in the middle. And I have 3 oxygens. So 1, 2, 3. I keep writing so big. I don't know why I keep doing that. I'm so used to spreading things out because I use the board and Okay, let's see. Now I have to count the number of elements I have. So I need my valence electrons. I'll do it on the side over here. I have nitrogen in the compound. I have oxygen, and I have a negative charge. I have 1 nitrogen. Nitrogen is in group 5. So that gives me 5 electrons. I have 3 oxygens, which are in group 6. That gives me what? 18 electrons. I have the extra electron here from the negative charge. This is 1 times 1, essentially 1. Okay, when you have a negative charge, that means it's excess electrons. When you have a positive charge, you're missing electrons, so you will subtract. Okay, so here, yeah. Okay, I add these. Where's my calculator? I know I can add them in my head. I realized something about my brain. When I do a lot of different things, my brain gets fatigued. When I started teaching online like this, every click was a burden to my brain, so I get so fatigued. And I was really struggling. It took a while for my mind to get used to all the clicking. That was like a lot of extra functions for my brain. It's like, oh, click, swipe. Now I'm doing a lot better, way better than last year. Oops, don't add this yet. Okay, so here we are, right here. 24 lessons to work with. I put a single bond here, single bond here, single bond here. That's what? 6 electrons minus 6. So I'm keeping track of this minus 6. That's why I have my calculator right here. I'm left with 18 electrons. Make octets of the surrounding elements. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 3, 18 minus 18. Look at that. Man, we finished the electrons fast. Check for octet. 6 electrons plus 1 bond makes 8 electrons. 8 electrons. 8 electrons. Central one only has 6, right? Okay, we're now going to help the central one get to octet. But we have 3 possibilities, right? Sorry, I'm drawing the arrow because I know where this is going. We have 3 possibilities. We have 3 equal oxygens to help out the nitrogen. So one possibility will give us resonance A. The second possibility will give us resonance B. The third possibility will give us resonance C. Okay, so the first possibility, I'll just use the oxygen on the left. So if the oxygen on the left is helping out my nitrogen, I'll draw it like this. I'm trying to draw a little smaller. And this oxygen, this oxygen, this oxygen. Let me just copy them all out so I can do well with space. Okay, because I do have spatial issues, as in I use too much space and I have to kind of shrink the structure. Okay, this is where we are, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, fine. Now, the one on the left for resonance A is the one giving up its electrons. Let me see if I can erase this with no problem. Oh, they're gone. Good. That's the one helping nitrogen in the middle. Okay. And then next to that, I have for resonance B, the one on the bottom is a sacrificial oxygen. Oops. Okay, it sacrificed itself too. Back here, the one helping the nitrogen. Then the one on the right will be the sacrificial oxygen. Oh, okay, that's okay. I'll redraw it. This one here is helping the nitrogen. So you can see, right? Essentially, once I'm done with resonance A, B, and C, I end up with 3 different structures. I'm not done yet. I mentioned this on Monday that when you have a negative charge or positive charge, when you have a polyatomic ion, you have to include the charge in the Lewis structure. So Lewis structure technically has brackets and a charge. Brackets and a charge. Brackets and the charge, right? The charge has to be written on top right. Not only that, and then we have this, the the resonance arrows, right? This. So we know these are 3 Lewis structures of each other. Okay, so we have resonance A, we have resonance B, resonance C. So essentially answer the questions they were giving us, Lewis structures and their resonances. I said, let's go ahead and add the hybrid. We've come this far, why not? So we'll draw the hybrid. Ooh, can we draw the hybrid? I'll make it real small down here. The hybrid. Keep the central atom where it is. Keep the surrounding atoms where they are. Keep the single bond where it is. Single bond, single bond, single bond. And then take the one double bond you have and spread it around to all the connecting molecules. Everywhere the double bond was in the original molecule. So we had the double bond here, we had it here, and we had it here. So now you're taking the one double bond and then dividing it 3 times and then spreading it around. Okay, so dot, 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 dot. So when you're asked to what's the value of this hybrid, what's the value of the bond in the hybrid, you would say it's 1/1/3 or 1.33. Why? I had to take the second bond in the double bond, divide it by 3 and equally spread it around. Okay, so divided by 3, you get about 0.33. So each of these hybridized bond has a value of 1/1/3, right? So there you want to know your fractions. Most of the time it's either half or 1/1/3. I mean, they can give you a hypothetical scenario where it's a quarter, so you're dealing with like 1.25, something like that. But Yeah, so here they show you the resonance structures, and then you have that there. You can practice this on your own. So this tells you the rules of drawing resonance structures. In your resonance structures must have the same connectivity, meaning you cannot rearrange the atom so your central atom is now the outer atom. You can't do that. Only the electrons' positions can change. Resonance structures must have the same number of electrons. Remember, the only thing you're moving around at our level is the second bond of the double bond. Now we're moving on to something called the formal charge. So kind of halfway through this paragraph, the focus changes to the second concept, right? That's the formal charge. So now we're saying, what if the Lewis structures are not like resonance structures, which look like they're the flip form of the same formula? What if the Lewis structures look very different? How do you judge objectively who is more correct? So let's say I draw a Lewis structure, you draw a Lewis structure, and then I argue with you because I'm the teacher, I'm right. And then you're like, yes. You shouldn't just say yes. There has to be an objective way for us to tell that I really am right, right? When I tell the story, I'm always the right one. Anyway, they're telling you how you do it here. The better Lewis structure. So we'll assign something called formal charges. Formal charges aren't the same as a regular charge, right? Listen, guys, it's okay to have that running dialogue and commentary because I still do in my life. Okay. When I was learning this in school, I was like, wait, what? Formal charges are not the same as regular charges. Formal charges are something that we do because we have one goal in mind. We assign formal charges to elements to figure out the correct Lewis structure and to figure out which charge or which element in the compound has the negative charge or the positive charge. Okay. So before I continue, let me write that here. Formal charges are assigned to elements to determine best Lewis structure and charge of element within compound. And this will make more sense when we're actually working this out, right? You're like charge of element within the compound. Yeah, sometimes we're trying to figure out which of the elements actually has a negative charge or which one is more like a negative, right? Okay, so number one, better structures will end up having fewer formal charge. Once we assign the formal charge, we will judge the better structure as having fewer formal charges. We'll say better structures have smaller formal charges. Better structures have the negative formal charge on the more electronegative element or atom. Okay, so we'll go over that once we are done assigning this. Okay, so we've got lots of words here, and we're told if you have a compound that is neutral, the sum of all formal charges in the neutral compound must equal 0. The sum of all formal charges in the ion must equal the charge of the ion. Once again, as we are working this out, these rules will make sense. Okay, small zero formal charges on an individual atom are better than large ones. When formal charges cannot be avoided, negative formal charge should reside on the most electronegative atom. Okay, we're going to be working this out as we work on, let me see. I want to work on more difficult ones, so I'm going to start with, let me start, let me see, hold on real quick. Yeah, let me start with this one here, just because I'm trying to work a few examples and not all the examples because of time. So I'll start with this situation here and say, using formal charges, decide which is the best Lewis structure, HCN or HNC. So apparently, it is possible to draw a Lewis structure for the formula H, C, and N and draw it this way and this way. But of course, one is better than the other, right? So let's go ahead and examine that. And I'm going to draw this down here. I'm going to try to mimic what they have, okay? So we're going to have the Lewis structure. For the first one, we're drawing HCN. Of course, remember we're doing versus H and C. Okay, so let me see how they have it. I like to do mine by element. Okay, so before I go into all this, I forgot to define one thing. What's the formula for the formal charge? So before we go into all of this, the formal charge is usually abbreviated FC. So like FC, formal charge, is equal to, we start with valence electron minus uh, lone pair electrons. And then what they have here is half the number of bonding electrons. I'm going to give you guys a simplified version, okay? So valence electrons minus lone pair electrons minus number of bonds, okay? So I'm going to say here, as I abbreviate and make this formula simpler, formal charge equal valence electron minus lone pair electrons minus bonded electrons. So this is all about electrons, okay? And when I'm working this out, I will keep saying this word, valence electron minus dots minus lines. Okay, it's just a paraphrase, but this helps me to visually see what I am doing. Remember, lone pair electrons are shown as dots, right? So you don't have to remember it that way. When I'm working it out and I'm translating from one point to another, because I do a lot of twists and turns, I'm trying to make sure I'm not getting confused. And I'm trying to make sure what I'm seeing visually is confirming the process. So I usually say minus dots, minus lines, just in case you're wondering what I'm saying. I have translated it here. Bonds are shown as lines. Lone pairs are shown as dots. Okay, so now that we have cleared that up, I think I'm ready. I'll start with HCN. So for HCN, I'll start with, let's see. I don't know why, because I saw the way they did theirs. Is this how I want to do it? Yeah, it's okay. So I'm going to start with, I guess I started with the proper form, hydrogen, and then we'll do, yeah. So hydrogen, we'll do carbon, and then we'll do nitrogen, right? So for hydrogen, I will have my valence electrons. I'll have my number of lone pair electrons, and I'll have my number of bonded electrons. And then we'll work all this out, and we'll see how this works out, okay? So for us to see how this works out first, you have to actually draw the Lewis structure for HCN. So real quick, hydrogen, 1 electron. And we only have 1 in the formula, right? Carbon, we only have 1 in the formula, 4 electrons. And so this is going to be 4. Nitrogen, we only have 1 in the formula, 5 electrons, based on the group numbers, so 5. So I'm working with how many electrons here? 10 electrons. So you have to have your Lewis structure drawn. I almost forgot to mention that part. Okay, central atom based on this right here, carbon in the middle, nitrogen, and hydrogen. Form a single bond. Single bond. Single bond uses how many? 4 electrons. We're left with 6. Put the 6 electrons on nitrogen, not hydrogen. Hydrogen cannot handle any more electrons except for a single bond. Okay, nitrogen currently has the pattern that says it has octet. Carbon doesn't. Carbon has 2 bonds. That means it only has 4 electrons. We need to get it to 8. So to help carbon get to 8, take the electrons from there, form a double bond. Carbon now only has 6 electrons. Do that again. Take these electrons here. I'm going to bring back the N. And so in doing all that, we end up with the following. Okay? So we have hydrogen, carbon, and nitrogen. Oh, I forgot my lone pair here. This is like that. Now, hydrogen has 2 electrons, carbon has 8 electrons, nitrogen has 8 electrons, right? And you can see the combination around them. Okay, let's start with hydrogen. So this was all to do my Lewis structure. I have it here. Now I have a visual, right? So let's see what's going on with the hydrogen. What's the valence electron objectively for my hydrogen? Let me erase all this so it's not confusing. Hydrogen is in group 1, so the valence electron is 1. Let's look at the structure right here. How many electrons do we have around the hydrogen, or how many lone pair electrons surrounding the hydrogen? Do we have any dots around the hydrogen? No. So I'll say 0. So remember, it's 1 minus 0. So this minus this. And then how many bonded electrons, or in this case, you could just say how many bonds, or how many lines do we have attached to hydrogen? We just have 1. So 1 minus 0 minus 1 equal 0, right? 1 minus 0 is 1, minus 1 is 0. Okay, next one. Carbon. So now we're examining this carbon here. What's carbon situation? Carbon is in group 4, so it has 4 valence electrons, right? Subtract the number of lone pairs around carbon. Does carbon have any dots around it? No, so 0. And then subtract the number of bonds around carbon. So once again, even though I have B here, BE here, if it's better for you, you can just write the word bonds. It's a lot easier. That works. But once again, I told you I use lines. So how many lines do we have in contact with carbon? We're looking at carbon right now, right? How many lines do I have in contact with carbon? 1, 2, 3, 4. So minus 4. So I got 4 minus 0, that's 4. Minus 4, this is 0. Finally, I have nitrogen. Nitrogen is in what group, or what's the valence electrons? I have 5. Okay, how many dots or lone pairs do I have around nitrogen? Oh, now we can see a difference, right? Finally mixed it up. We got 2. In this case here, you're not looking at electron groups, so don't group them and say 1. That's why I said dots here, just to help you all out, okay? Because in the big picture, when you're trying to combine all this stuff, all the little minute details get lost and it just falls apart. So you want to find a logic that you know your brain will hold on to even when it gets smooshed with everything else. Okay? This is my logic that works. Dots, lines, count lines. I can do that, right? Where was I? Around the nitrogen, we have group 5 minus 2 dots minus 3 lines. 5 minus 2 minus 3 equals 0. So I'm going to tell you right now, 0, 0, 0. Okay? So back here, somewhere, in a lot of words, somewhere, they said, first of all, make sure the formal charge is in the neutral molecule at 0. If you have an ion, the formal charges must equal the ion. The better structure, as small or 0 formal charges on an individual atom are better than large ones. So it's a fancy way of saying we would rather all the atoms in the compound have a 0 formal charge. Okay, so I'm just going to tell you right now, this is a really good structure. Okay, so we're done with this structure. What about the other one, the runner-up, I guess? So this is really good. The other one's got to be the runner-up. The runner-up structure was H and C. How do we even draw H and C? I'm running out of space again. H and C. Once again, Lewis structure. Same combination we had here, right? We had 10 electrons. So we'll start with 10 electrons. Remember, hydrogen is in group 1. We just have 1. So this is 1. Nitrogen, group 5. We have 1. So this is 5. Carbon, group 4. We have 1. This is 4. You add all this, we have 10. Okay, now join the Lewis structure. This time N has to be in the middle because we have to match this structure, right? Then carbon, am I going to have enough space? Okay, N in the middle, carbon here, hydrogen here. Draw a single bond, single bond, single bond. 2 times 2 is 4. Minus 4, we're left with 6. The 6 electrons go on the carbon because they never go on the hydrogen. So 1, 2, 3, 4, 5, 6. Okay, this now has 8 electrons, and then the nitrogen in the middle has 4. Hydrogen has 2. Hydrogen is happy. Nitrogen is not. So remove the electrons from here. You put them here. Remove another pair of electrons from here. Oops. Man, struggles. There. Okay. So it's just like what we had before, only this time, this is what we're dealing with. Okay. So we're going to check this out and see how this works out. So I'm going to write it as H, and I'll go in the order of how it appears in the formula, N and then C. Okay. So we're doing this, and our formula is going to be valence electron first, right? And then what was it? Lone pair electrons minus lone pair electrons minus bonds, right? We're doing this setup right here. So starting with hydrogen. Hydrogen is in group 1. Number of lone pair electrons, aka dots, 0. Number of bonds, 1. 1 minus 0 minus 1 equals 0, just like what we saw before. Okay, next one. Nitrogen. Valence electrons, 5. Number of lone pairs, I see none around this, right? So there's 0. Number of bonds, which is the same thing as number of lines. This is 4, right? 1, 2, 3, 4. Okay. 5 minus 0 is 5 minus 4 is 1. Ooh. Okay. Now last one. Carbon is in group 4. Minus number of dots, we got 2. Lone pairs are dots, right? Minus lines, we got 3. 4 minus 2, 2. Minus 3, negative 1. Ooh. Okay, so what we're saying here is, first of all, conclusion. This is a better better Lewis structure. If you draw that one, you win. This is not as good. Why is this not as good? Because when we're done assigning formal charges, we now actually have formal charges on N. So N in this structure is going to be positive 1, and then C, based on the combination, is going to be negative 1. So this is how you draw formal charges. Formal charges are drawn in little circles like that because they're not regular charges, right? This compound here is neutral. It doesn't really have a charge. So when you put a formal charge, you have to put it inside a circle, okay? So by virtue of this and this is a better Lewis structure, okay? Okay. Oh, I'm sorry. They did theirs up here. I forgot. The table is up here. They show you this is a much better Lewis structure. This wins. So we're going to do this again on this next one. Oh, yeah, this next one right here. So in this next one, let me see. I'm going to try to do them both on the same page if I can manage that. Yeah, they do it horizontally this time. I don't know why they did it vertically the first time and then horizontally the second time. Oh, they were doing it vertically. My bad. Okay, they're doing vertically. So this time, I wonder if I can do it here and do the valence electron for the element, number of lone pairs, and the number of bonds, right? Remember, lone pairs here are essentially the dots. Bonds are the lines, right? And you're subtracting this. I think we can do it. Okay, so for OCN, they give you 3 different possibilities, the first, the second, the third. We're going to go with this. I'm trying to figure out which has the best Lewis structure, right? So I'm kind of shorthanding this because of time. So the group number for oxygen is 6. Group number for carbon is 4. Group number for hydrogen is 5. So you want to have a periodic table so you can look at this real quick, right? So the valence electron for oxygen will be 6. For carbon, 4. For nitrogen, 5. So I can actually go through and kind of place these on that, right? Oxygen, carbon, 4. Nitrogen, 5. Oxygen, 6. Carbon, 4. Nitrogen, 5. Part will not change. Now we're going vertically, right? We're looking at the number of dots around the elements in the Lewis structure. So I'm going to draw divider lines. I need that. I prefer that. I like what I'm writing to be visually sorted out. Okay, so we're starting with this first one. We're looking at oxygen. It's our situation right now. Oxygen has dots, right, surrounding it. I see 6 dots, 6 lone pair electrons. So you're subtracting that. And then it has how many bonds? I see a bond. subtracting that. So 6 minus 6 is 0. And is negative 1. Okay? And then carbon. We start off with group 4. How many dots around the carbon? None, right? So this is what we're looking at right now. None. How many lines though? I see 4. So you're subtracting this. 4 minus 0 minus 4 is going to be just 0. And then what about this last one? Nitrogen. Nitrogen is in group 5. Minus the lone pair electrons or dots, we have 2. Minus the lines, we have 3, right? 5 minus 2 minus 3, we have 0. So in this structure, once I've done all this, carbon and nitrogen have no formal charge. Only oxygen has a formal charge. So this would be minus 1. We'll go on oxygen. The rest of them are 0. Okay. What about this arrangement of the bonds? Let's see. Once again, the valence electron, we already have those written down. So oxygen in this combination here has 4 dots around it, 4 lone pairs. Sorry, not 4 lone pairs, 4 electrons in the lone pairs. And then 2 bonds, right? 2 lines. 6 minus 4 minus 2 is 0. The carbon in the middle has no lone pairs, so minus 0. It has 4 lines of 4 bonds, minus 4. 4 minus 0 minus 4, 0, right? Nitrogen, group 5, minus 4 dots, minus 4 electrons in the lone pair, minus 2 lines, minus 2. You see why I like to go by things that help me to focus when I'm going all over the place, right? Yeah, it took me a while to kind of develop that skill. When I say a while, because I had chemistry ever since we were in middle school, so yeah. Where was I again? Exactly. 5 minus 4, I'm left with 1 minus 2, negative 1. Okay, notice you're getting a negative 1 formal charge each time. Because you have a negative charge, one of them has to be, when you add all the formal charges, they have to equal negative 1. So negative 1 plus 0 plus 0, negative 1, because you have a negative charge overall. So this time the one that carries a negative is nitrogen. And then last combination, oxygen, group 6, number of dots to subtract 2 from lone pair electrons, number of bonds, 3. So 6 minus 2 minus 3 plus 1. Carbon, 4. Number of lone pairs, 0. Number of bonds, 4. 4 minus 0, 4. Minus 4, 0. Carbon tends to like to be 0. Have you all noticed that? I'm like, okay, carbon. Nitrogen is 5, group 5, right? Number of dots around it, 6. Number of lines around it, 1. What? Okay, 5 minus 6 is already negative 1. Then subtract 1 again is now negative 2. This is, I can tell you right now, not a good structure. Okay, so if you add the formal charges according to one of the rules, excuse me, the total formal charge has to equal the charge on the formula. The formula has a charge of negative 1. So plus 1 plus 0 minus 2. You add that up in the calculator. It's minus 1. So where was I? Here, this is plus 1. Here, I got 0. Oh, this is minus 2. I'm only putting the formal charges, right? So after you're done with that, you get to be a judge. What's the worst structure ever? So they said in the rules, the best or the worst Lewis structure has too many charges assigned to the element. Okay, so A and B only has 1 charge assigned to 1 element. C has 2 charges assigned to 2 elements. So this is not a good Lewis structure. Doesn't really, I mean, yeah, it's not very good. I was trying to rationalize. I said, nah, it's just not a good structure. So now we have these two to compete. Okay. So I want to go back and look at the rules back here. What does the rules say? Oh, there. So we said once again, you want to have small or 0 formal charges. So rule number 3 on individual atoms. And these are better than having the large ones. Okay. So A and B both have formal charges. So it says here, when the formal charge cannot be avoided, the negative formal charge should reside on the most electronegative atom. Most electronegative. So let's go back and find out which is most electronegative. Oh, okay. So we're looking at this. We're looking at oxygen holding the formal charge versus nitrogen. Which is more electronegative? So with this one here, I usually pull out the periodic table. I don't have it here right now electronically, so I just go with, in the periodic table, this is the order of the elements, right? Going through the most electronegative, most E nev, that's electronegative, E neg. Electronegative, I'm like, what is nev? E neg, okay. Oh, my brain. Anyway, so fluorine is the most electronegative. So in the order, when you're going towards fluorine, fluorine is the most electronegative. So that means between oxygen and nitrogen, oxygen is more electronegative than nitrogen. So this structure wins because the best Lewis structure has the most electronegative element holding on to that negative formal charge. So this would be the first, this is the second runner up, and then this one is like bad. Okay, so they kind of explain all that. Structure A is preferable to B because it has a negative formal charge on the more electronegative atom. So the way they say this is you should expect A to make the biggest contribution to the resonance forms of cyanate ions. So that ion is called cyanate, and so the idea here is A, B, and C are all contributing to the best structure, the overall structure of cyanate ion. Because A is the most stable structure or the best structure of the three, A will make the most contribution to the final structure. That's how they say this. Okay. Oh, and then they have an example here. I won't go into all of this one to draw this, but I'll show here since they already have it. I'll just walk you through it. They had 24 electrons to distribute. They did it here, right? When they got to the stopping point, you have to add double bond to the central nitrogen. You can add it here to make one resonant form, or you can add it here to make the second resonant form. Y'all know how this goes. So they showed it here. They show you the true resonance form, very neatly drawn, better than my pictures. I'll call this res A, resonance A. This is going to be res B, resonance B, as you see them over here. Remember, they use the formal charge rule. Oh, they're using the formal charge rule here to figure out which is the best resonance structure. And in doing so, of course, you can see here, you have the valence electron. So oxygen has 6 valence electrons, right? Number of dots, 6. 1, 2, 3, 4, 5, 6. Number of lines, 1. So 6 minus 6 is 0. Minus 1 is negative 1. Nitrogen is 5 minus 0 lone pair electrons minus 4 bonds, positive 1. So here we have negative 1 here, positive 1 on nitrogen. And the rest of these, because they've shown nothing on them, these are 0, these are going to be 0, these are going to be 0, these are going to be 0. So they're showing you what's going on here. When this top oxygen doesn't have a double bond, the formal charge is negative 1. When it has a double bond, formal charge is 0. Nitrogen has 4 bonds, so formal charge is plus 1. Okay. Oh, so now we're moving on. As I'm looking at this, I'm like, wait a minute. Now we're moving on the thought. We've gone over resonance, we've gone over formal charges. Now we're drawing Lewis structures for compounds that have expanded octets. So we mentioned this before. When you go to the periodic table, remember group 3 elements, not group 3, period 3 elements on the P block, they're able to actually have expanded octet. So how do you know that the central atom has expanded octet? This only happens as the needs arise. So let me show you a scenario, okay? We're working on this one here, XEFE. And the lab that y'all have to turn in, the one with the Lewis structures, you will have to know which ones have expanded octet. So here's an example. We're following the rules, right? We're kind of blindly following the rules. rule says. Since you have one xenon that goes in the middle, you have two fluorines that go on either side, right? Hold on, let me drink some water here. What's our total valence electrons? Our valence electrons are, so this is valence electrons. I have xenon in the middle. This is going to be what group? 8. Okay, we have one xenon. Let me stick with the format. One xenon, and that's in group 8. And we have 8 of these. And then we have, in our formula, 2 fluorines. And each fluorine is in group 7. So 2 times 7 is what? 14. When I do all this chemistry, I forget the simple things, left to right, adding. So I have to use my calculator to give my brain a break. Oops. 8 plus 14 equal 22. We have 22 electrons to distribute between these 3 atoms, right? Okay, form a single bond here, single bond here. That uses up 4 electrons, so minus 4. I'm left with 18. Okay, 18 electrons. Follow the rules. Add 6 electrons to the peripheral elements. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 2, I did that twice, right? So minus 12, minus 12, minus 12. I'm left with 6. Okay, now the rule says once the outer elements have an octet, then whatever's left over, kind of dump it on the central one. Doesn't really use the word dump, but you know what I mean. You have to put them in pairs though. So 1, 2, I've got 6. 3, 4, 5, 6. Minus 6, I'm at 0. Okay, so let me check to see if I have an octet. The surrounding ones have octet, right? 6 electrons as dots, and then 2 in a bond. So they have 8 electrons here. Here we have 8 electrons. But what about the central one? The 2 electrons here, 2 electrons here, 2 here, 2 here, 2 here. 1, 2, 3, 4, 5. The central one has 10 electrons. This is more than octet. So you can say xenon has an expanded octet. It has to expand its octet to be able to accommodate all the extra electrons that were brought into this relationship. Okay. So when I was a student, I don't know why. You know, I blame it on biology, not the teacher. It was my misconception. And then plus, the chemistry teacher wasn't clear to say, don't try to memorize all this. I was copying other people because I didn't know any better, and I tried to memorize all this stuff. If you follow the rules, it plays itself out which elements have to have expanded octet versus trying to memorize. This one will, this one won't, because when I was memorizing it, sometimes it wasn't working out. So I was really not doing very well by virtue of trying to learn chemistry like it was biology, right? Use. Right. So when you follow the rules, which is why the rules are very important, it plays itself out. You can see right here, xenon has more than 8 electrons. Oh, molecular geometry. Okay, so once we've done all this stuff, now we're going to molecular geometry, like it states right here. Geometry, when it comes to math, because there's a similarity here, it's called geometry because we're dealing with the electron groups rearranging themselves differently around the central atom. So what we're going to be looking at right now, geometry, we're looking at geometry. Focus is around central atom. So there's always an atom of focus, right? You're focusing on this atom and you're being asked what is going on around it. Kind of like what we did with the formal charge, right? So for us to transition to the electron geometry, we have to look at the VSEPR. VSEPR, which is pronounced Vesper, is valence shell electron pair repulsion theory. What this is saying is the valence shell electrons, the ones in the group, the valence electrons, these, they are arranged around the central atoms in pairs. But since they are electrons, meaning they're negative charge, because they have the same charge, they will repel each other. So what they're trying to say is, using this picture right here, say this is your central atom, right? And your central atom is bonded to three other atoms. So instead of showing the bonds as bonds like lines, they're trying to show you that the bonds are technically made up of electrons. Remember, 2 electrons per bond. So they're showing you here that because the bond is technically made up of electrons, and electrons are technically negatively charged, then when you have negatively charged groups next to each other, because they have the same charge, they will repel each other. Same charges repel, opposite charges attract. The molecule still has a goal. Goal, stability. So how is the molecule be stable and have all this repulsion going on? Because repulsion is kind of like conflict. Repulsion in the world of the molecule is conflict. It's hard to be stable when you are at war. So this theory says that electron groups around the central atom will most when they stay as far away from each other as possible. So when they're as far away from each other, because you're trying to minimize the repulsion, right? The repulsion is kind of like conflict when you have, groups that will naturally repel each other to, they stay away from each other as far as possible to conflict, aka repulsion. So it says because the electrons are negatively charged, they should be more stable when they are separated as much as possible. And because of that, the way Lewis structure do the bonds, all neat, all vertical, all horizontal like that, you have a central atom, you have this here, and this here. The way he drew that is wrong. Lewis is wrong. Lewis was wrong. Okay? Because Vesper theory says when you have bonds around each other and bonds are technically negative, they'll repel each other and then they'll come up to a natural arrangement where there is minimum energy. So that results in bonds being at an angle that's not necessarily 90 degrees. Okay? So we're being told here that the Lewis structure predicts that the number of valence electrons pairs are usually around the central atom. We're told each lone pair constitutes one electron group. So here we're trying to see how to actually read through this, right? And because I don't have a lot of time, what I'm going to do is I'm going to jump to the handout I gave you guys in the lab. I think that was in the lab, right? Yes, I'm gonna jump to that, and that will help us kind of learn this really quick in a shorthand way. But we're gonna have to learn how to count the number of electron groups around the central atom. So we're being told here in counting the electron groups, and let me add a new page. Oh, stop moving. To understand how electron groups repel each other, comma, we shall count electron groups around the central atom. And so here we're going to count. How to count electron groups. Okay? As I said, from here I will navigate to, because I'm looking at how much time I have left, I will navigate to that table in the lab. I really think it's in the lab. So we will discover this together. We'll go on a discovery. Number one, so you're looking at your central atom, your focus atom. So the example they gave us here to help us count was the nitrite atom. So I'm going to draw this here real quick. The nitrite atom, you have that, you have that, you have this. Okay, so remember, nitrogen and oxygen, these are all elements that normally form octet, right? So having these bonds here, this oxygen has 2 electrons. I need 6 more electrons to make octet, so I add 1, 2, 3, 4, 5, 6, right? Nitrogen has 6 electrons. I need 2 more to make octet. 1, 2. Oxygen has 4 electrons. I need 2 more to I need 4 more to make octet. 1, 2, 3, 4. And then this has an overall charge of negative. So I put negative here. Okay. How do we count electrons? We're told one bond or single bond counts as one electron group. Double bonds, one electron group. Triple bond, one electron group. Lone pair, one electron group. Okay? Okay, y'all know how I share my experience, I share my past, and I share my struggle. Okay? Because I told you guys, language is not my strong suit. I actually ask a lot of questions because just language is not, it's just never really been one of those areas where I was really good at it, right? So I'm following along. I'm like, okay, yes, I'm with you. And I'm like, okay, wait. One bond or a single bond is one electron group. Double bond, shouldn't that be 2 electron groups? No. And the teacher and I are not having this dialogue, so I'm having this with myself. I'm like, no. Look at them as if they're drawn together, they're groups together. That's how I was able to survive this logic. I feel like I have an unusual way of seeing things because I just say it's unusual because you should see the looks people give me when trying to explain stuff. They're looking at me like, I'm like, okay, I guess the way I'm thinking about this is unusual. Okay. But even though I struggle with this so much, my grades were stellar. Okay. Because other people weren't struggling with this, so I guess they got it, but apparently they didn't. But no, one bond, single bond. So if you think differently, don't feel bad. The point is work hard at it and then do well. That's all that matters. Okay? Do you, be you. So my rationale here was when they said group, they meant group. If the lines are grouped together, count them as one. If the dots are grouped together, count them as one. That's why lone pair counts as one group. So the dominant term here is the groups. And that's what helped me with this. So I'm going to highlight the groups, right? These are together. These are together. These are together. Remember, our focus is a central atom. So based on this, we end up having a group here, a group here, and a group here. 3 groups. Now, it wasn't explained this way when I was learning it, so I'm like, I see 4 groups. Or if you split the electrons, I see 5 groups. I was seeing a lot of different things, y'all. It was a trip. But anyway, no, these are 3 groups, okay? They're grouped together. So, since we now have an idea how to do this, I want to, as I said, take a shortcut. And to help you guys work on your lab, 1411, I think I have this I'm working on a new class that just started. So because my focus is there and it's not here, where are we going? Oh yeah, this is the one that you guys are working on right now. You probably have already worked on it. Maybe you haven't. Molecular structures. Yeah, this one. The help document. So in order for you to do the molecular geometry, it does help if you have the lowest structure. So I'm just going to tell you right now, the order is you want to have your lowest structure drawn so you can know your central atom that you're focusing on, right? Because if you don't have your central atom, your lowest structure, how do you know what you're focusing on? Look at that. We went straight into this. Let's see, draw feature. Okay. Yeah. So here, note, electron pairs shared between atoms, single bond. This counts as one electron group. Everything here is one electron group. As long as they group together, they're one electron group. And then here I also show you, sometimes people use this notation, like the format. And if they do, they say A is central atom, B is a surrounding atom, L stands for lone pair electrons. Now for you guys, your lab didn't really have that. I gave you guys an example here of how these were grouped together, right? This is a group. This is a group. Oops. This is a group. That's a group, and that's a group. Okay. 2 lines and then 2 sets of dots. So oxygen electron groups, 4. Okay. So let me make this slightly smaller. When you're trying to do this, I gave you examples, right? When you're trying to work on this, work from left. This is left. I hope you can see my little mouse thing here to right. And I even showed you how to figure out what is polar, what's non-polar. Okay. So for this one here, you can see carbon is in the middle, right? Surrounded. This is a Lewis structure. So I should call this Lewis structure. How many groups do we have here? There's a group here, and there's a group here. Just 2 groups, right? You can see how the double bonds are grouped together. So they are a group there and a group there. So we have 2 groups right there. You're reading across. So you want to have your Lewis structure. If it has 2 groups, how many of those 2 groups are bonded groups? It shows here, both this one here and this, they're both bonded groups. There's no dots around the carbon, so both are bonded groups. There is no number of lone pairs around your central atom. Remember I told you guys, everything we're doing here is around an assigned central atom. Only carbon is central here. We have 2 groups. Both groups are bonded groups. We have 0 lone pair. If that's your situation with your compound that you just drew, then the bond angle, the angle between the bonds is going to be 180. The geometry of this compound, based on how the elements are written, if you draw it out like this, carbon, oxygen, oxygen, and it kind of looks like this will be linear. Okay, electron pair geometry will be linear. And then molecular geometry, which is another term for the shape, this will also be linear. So please note, molecular geometry is what they call the shape. They never call electron pair geometry the shape. So sometimes they say shape. It took me a while. I'm like, if they're just saying shape, they mean this or this. No, molecular geometry is the shape. So when you have 2 groups around the central atom, the groups will rearrange themselves so that they're 180 degrees away from each other, as far away as possible, and you will have a linear geometry. If you need the molecular type, it will be AB2. Remember, the A stands for the central atom, B, the surrounding atoms. We have no lone pair in the central atom, so this would be A, B, 2. Okay, I have to explain the nonpolar because I recognize you have an exam coming up and we will not meet again until the exam is done, right? Okay, later on in the chapter, we cover polar and nonpolar. Usually nonpolar molecules are nonpolar because once you draw your Lewis structure, you examine the surrounding atom. Nonpolar means symmetry, no difference. Okay, so nonpolar, because remember polar means different. Nonpolar, non-difference, pretty much same. Okay, look at these elements, surrounding elements. They're the same. It's O and O. It's not like O and S. If it was O and S, this would be automatically polar. So this is nonpolar because the surrounding elements are the same. And then the other thing is there is no lone pair on the central atom because lone pairs introduce a different surrounding group. So to determine polarity, we're looking at 2 things, okay? For polar, we're looking at, surrounding groups. Sorry, it's hard to write with my mouse. If they're different, the molecule is polar. And we're looking at electron groups. All right, here, elect groups. If the surrounding electron groups are different, then we can also say the molecule is polar. As long as we have a difference, we have polar. You can see the surrounding groups here are the same, double bond, right? Bond, bond, no lone pair. Okay, so this is going to be nonpolar. Okay, so let me stick with one thing. Okay, let's go through and examine the nonpolar ones. Nonpolar. Surrounding groups are all alike. Cl, 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 Cl. Bonds match. Match, match, match. Right? We said this is polar. Why? Central atom has a lone pair. The lone pair introduces a difference around the central atom. When we have differences around the central atom, difference equal polar. Here we have the same group, same type of lone pair. Same type of bonds, nonpolar, non-difference. Here we have a difference here, polar, two lone pairs, polar. These are different from that. Okay, it's kind of a simplified version. I even found this on purpose to try to tell you that it doesn't always have to be about the um, lone pairs. If one of the surrounding elements are different, like this one here, one of these things is not like the other, polar, because polar is another word of saying different, right? Here, the surrounding group is different. And then here, these are not like the bonds, so polar, right? But please, even though I'm going through this, you want to go through and kind of make sure you understand. Now, the rule I gave you about determining polar has exceptions, and here's where we have the exceptions. In this scenario here with xenon, even though the lone pairs are different from the bonds, the positions of the lone pairs are such that the effect these do on the bonds cancel each other out, which I wrote over here to explain it. Therefore, the overall molecule will have a bond angle for the remaining bonds of 180, and they will end up being nonpolar. So this is where that rule falls apart. And I gave you guys a rationale right here. This is kind of a shorthand, quick way, right, to get the answers. And then I finally end. And then these, another exception to the rules, two lone pairs, but the position of the lone pair is they're usually above and below the molecule. The way the lone pairs position cancel each other out and the effect they have on the molecule, okay? So if you're wondering what effect the lone pairs have on the molecule, the lone pairs push against the bonds. They're kind of like bully electrons. They push against the bond. Against the bond, like right here, when they push against the bond, they push the bonds a little closer. So if one lone pair out the other lone pair, then even though they're present in your picture, they act like they're because pair is canceling out the other. See that happening in those two scenarios. Other than that, draw your Lewis structure. Okay, so start from left to right, draw your Lewis structure, find which one of these your Lewis structure matches. I've given you all, I think, all the possible scenarios, almost all the possible scenarios. If your Lewis structure matches, say, this one here, you have a central atom, you have 4 surrounding atoms, and you have 4 single bonds, then you go through. Total number of bonds around the central atom or number of electron groups, you count here. You got 1, 2, 3, 4. All those 4, how many are bonds? All 4. How many are lone pairs? None. So what will be the bond angle between these bonds? You know, this bond here, not 90 is given to you. This will have a 3, right? So the bond angle here will be 109.5. And this will have a tetrahedral arrangement that looks more like this. So even though I'm giving you guys a shorthand version of figuring out the answers for your lab, please still go through the lecture. And I do have videos already posted. Please watch the video over the weekend as you prepare for the exam. Okay, I do have videos posted where I complete this whole lecture. So please go watch that one and go over it in detail. So yeah, tetrahedral here. And then, yeah, tetrahedral geometry. To me, I know. Listen, I decided in life I'm gonna be. Somebody said that you're a goofball. I'm like, okay, whatever. That's your opinion. I don't agree with that. But when I was learning this, okay, in Tanzania, East Africa, I'm like, this is giving me chicken claw vibes, right? Chicken claw. Okay, I'm trying to learn tetrahedral geometry in middle school. Okay, and I'm trying to survive. So I'm like, tetrahedral. chicken claw. I didn't really have personal experience with tetrahedral geometry. I hadn't seen a tetrahedron. My teachers didn't have a molecular model to show it to me. So when I saw this, I was trying to associate it to something I knew, and all I could think about was a chicken claw. Okay. Now I would say, because I know more, it looks like a tripod stand. Okay. A tripod stand is similar to tetrahedral geometry, but it's not as chicken claw still beats in my heart, you know. I'm just like, yeah, chicken claw, right? But a tripod stand will be more relevant to you guys more than a chicken claw. This one here has one missing bond on top, and the place it has a lone pair. So when you're counting this, you still have 4 electron groups, right? 4 electron groups. Of those 4 electron groups, only 3 are bonded groups. One of those groups is a lone pair. Because remember I told you the goal of the lone pair pushes more, it repels more on the other bonds. It occupies more space. So technically, even though I wrote 109.5, this may actually be slightly smaller. The bond angle may be 107, okay? Because the lone pair pushes more on the other bonds. And it's hard for me to visually show you guys this, but in your homework, some of the videos, it does show that to you. And so, yeah, 107, but the electron pair geometry remains the same. Electron pair geometry is based on the number of electron groups, regardless of what types you have. So this one is based on electron groups present. Okay, so based on that, even though one of the groups here was a lone pair groups, we still say you have 4 total groups, so 4 groups, and therefore this is tetrahedral. But when you're looking at the bonds only, you have 3 bonds and 1 lone pair. So imagine this one here with a missing top. The remaining bottom looks like a pyramid to scientists, so they call it trigonal or trigonal pyramidal. Sometimes they just kind of are lazy and they call it pyramidal. Some call it triangular. Be aware of all the terminology: trigonal, triangular, or just pyramidal. Okay, because it looks like a pyramid. This one here, this is an example from water, right? Water molecule fits here too. So with this one here, you have your central atom also surrounded by 4 groups. 2 of them are lone pairs, the other 2 are bonded groups. 4 groups. Of all the 4 groups, 2 of them are bonded groups, 2 of them are lone pair, right? And then let's see. Our bond angle here, I'm showing you the perfect bond angle, but because you have 2 lone pairs pushing against these bonds, actually what ends up happening is the lone pair end up on the same side. And then both of them are pushing on the bonds that are there. Even though I drew the Lewis structure, the Vesper model shows that these lone pairs push against the bonds like that, bending them. Okay. Somehow this reminds me of the abductor machine in the gym. I had to do that workout once when I was in track, and I'm like, hey, this reminds me of the lone pairs pushing against the bonded groups in the water molecule. Huh? Nothing. I know I'm weird like that. Huh. Anyway, so because these lone pairs are pushing against the bonded groups, the bond angle becomes so much less because these are being pushed closer to each other by these lone pairs that are trying to occupy a lot of space as they push each other. We end up with a bond angle of around 104.5. Okay. Because we still have 4 groups, the electron pair geometry based on 4 groups is still called tetrahedral, but the shape usually considers only the bonding groups, not the lone pair. Even though the lone pair bends the group, this one here is called bent. Okay, why bent? Because I try to make up stories because I wasn't there. When the scientists who were naming this see a shape that looks like a V, they're like, wait, this is not linear. Even though it looks linear, it's actually bent. We shall call it bent. I wasn't there, so I'm really making up this story, right? They thought it would be linear and the lone pairs would be opposite to each other like it's drawn here. But in reality, no, the lone pairs get on one side and push against the bond. So we end up with a bent structure, ergo bent. And then over here, when you have 5 groups, they arrange themselves to form a trigonal bipyramidal. It looks like two of the small pyramids stuck together, top and bottom. So something like this. It's hard for me to draw pictures, y'all. Oh, not bad. But you have the central atom somewhere in the middle, and you have 3 on the equatorial side, 1 top, 1 bottom. And so it's called trigonal because if you slice the middle in half, you get a shape of a triangle. Bipyramidal because it looks like 2 pyramids stuck together on the bottom. Okay? And so when you have a central atom surrounded by 5 groups, that's how they rearrange themselves. All the 5 groups are bond, no lone pair. Here they show you have 2 bond angles. In this case here, when one group is removed, it will be removed from the middle side. And so you end up with a structure, like for real, seriously. When the teacher said this in class, I laughed. That's me, that student. When he said seesaw, I was like waiting for him because my teacher didn't tell jokes. Seesaw, I'm like, you're joking, right? No, it's called seesaw. I'm like, you don't see the humor in this? They turn around. Oh, they turn around like totally ignoring, like, why is she in our class? I'm like, yo, they call this seesaw for real? Okay, okay. So seesaw structure, this is what I'm seeing. 2 kids sitting on a seesaw, right? Having fun. So back to the structure. One bond got broken. So the bond that was here got broken, and then this was got left behind. So somebody decided this reminds me of a seesaw, so we should call that structure a seesaw. See? I'm not the only one who sees things differently. And then once we remember we had this structure, we broke off one point, replaced it with a lone pair. In this structure here, the T shape, you break off another point, and then what you have left is something that looks like a T like that. And somebody said, that reminds me of a T. Really? Like, I think this is T, and they call this T-shaped. And then finally, so these shapes are all sort of, they are connected. You start off with 5 groups where all groups are bonded groups. And then as you go down the group, or down the series, that's why I had the same color. You're taking off one bond or you're breaking one bond and replacing it with lone pairs. So here, you still have 5 groups, but you break off one bond, replace it with lone pairs. Here, you break off a second bond, replacing it with lone pairs. So these used to be bonds, now they're lone pairs. Here, you break off 3 bonds and you're left with, and replace it with a lone pair. So once you break off this last bond here, you're left with a line. That's why it's called linear. Same thing over here with this green group. You start off with 6 groups, break off one group. So break off this one here, and then replace that bond with a lone pair. Then break off the other end, I guess here, and replace that with a lone pair, and that's how we get this. So for the 6 groups, we only have 3 variations. Okay. The one where all 6 are bonds, this is called octahedral. The one where 5 of the 6 are bonds, and then 1 is a lone pair. This is called, the shape is called square pyramid. It looks like a pyramid with a base as a square. So it looks like a square, and then it goes up like that, something like that. Yeah. Oh, not bad. Square pyramidal. And then here, you break that, the one that was coming out on the top, and you end up with square planar looking like this. The molecule looks something like this. The central atom and the surrounding atom. So it looks flat and it's a square. The lone pair here comes from the top and from the bottom. So go through, I'm kind of going through this part real quick, but if you go through the notes and I gave you examples here of how to read the groups and everything and examples. You will see how it plays out. You're pretty much in figuring out the geometry, reading from left to right. Once you judge what type, so you're going to use your picture of the Lewis structure and these first 3 boxes here to judge if your molecule has got 6 groups, right? So remember, we started with 2 groups. Let me summarize real quick. We started with 2 groups. With 2 groups, you only have one option. 2 groups, this is the only option you have. You don't have options. This is it, the one option. 2 groups. If you have 3 groups, you have 2 options. And try to categorize them by color. You have 3 groups where all 3 groups are bonds, right? or three groups where one of them is a lone pair. Two are bonds and one of them is a lone pair. So for three groups, you have two to pick from, this or this. When you have four groups, you have three to pick from. This is four groups, this is four groups, this is four groups. So find out which one your molecule matches with. Is it four groups where all four are bonds? Is it four groups where three are bonds but one is a lone pair? Is it four groups where two are bonds and two are lone pairs? Okay, remember, so we start with four, all four bonds. Replace one bond with a lone pair. Replace two bonds with a lone pair, and then we kind of degrade it as we go down. And then you have the different variations. And then when you have five groups, with five groups, I guess we have four different variations, right? You can see right here in the purple color. Five groups where all five groups are bonds. Five groups where only four are bonds, one is a lone pair. Five groups where three are bonds, two are lone pairs. Five groups where two are bonds, and then three are lone pairs. So you can see you're going down step by step by step. And the number of lone pairs go from 0 to 3, right? And as you're bringing in lone pairs, the name of the shape, only the name of the shape is changing. Of course, I should need to say only. The name of the shape changes, and then the bonds, sometimes the bond angles change because of the different bonds you have left over. And of course, the polarity will change too, right? Then back to the six groups, you have three different variations. Six groups, all groups are bonds. Six groups, five are bonds, one is lone pair. Six groups, four are bonds, two are lone pairs. Okay, so remember this table is in your help folder for your not homework, sorry, for your lab. So that will help you essentially quickly get to the end of the chapter to be able to do your lab. And of course, your lab is right here. And I think I gave you guys an example of how to work your lab. I did one for you. Oh, this is supposed to be completed. I'm like, what is complemented? Ah, completed, guys. I mean, complimentary is kind of like available for. No, this is completed. Oh, sorry. I'll fix that. This is what happens, right? When I'm trying to multitask. So yeah, this first one, oh my goodness. Right, number of valence electrons is 8. So remember, you start the hydrogen, there's two hydrogens, there's one oxygen, number of valence electrons 8. When you draw this, this is what we have here. With the Vesper model, you can draw it like this. This is a Lewis structure. You can do the Vesper model, or yeah, this works too. 3D drawing, either one works. And then you have molecular geometry bent. Is it polar or nonpolar? You write polar. In this case here, you have your lone pairs. Bond angle. I wrote 109.5. You can use 109.5 or you can use 104, right? And then you're doing the same thing for the second one. The second one here, you're just going in the list. So I did the first one for you. Completed, not complimented. Second one will be SiCl4. You do this one here, but just to give you a clue to tell you, you have no ClCl bonds in the structure. You're going to do this one. You're going in order from top to bottom. Okay, you're going through this. Any questions about this? So this is just in case you have not done the lab. Oh, sorry. Did somebody say something? Oh, that was just good morning. Any questions about the lecture or the lab? Okay, so this is all I have for today. I know I went over. I wanted to make sure you, because you have an exam coming up this weekend, that you have enough information. So when you're going over the homework, if you come across some questions, feel free to send me email, okay? Okay, guys, this is all I have for today. If you have no questions, he's stopping the recording.